Aloha. All right. Hope everybody is getting comfortable. In this time of transition, I'm getting comfortable myself, figuring out where to stand, what to do, what not to get blinded, and how to talk to myself. Great, you guys. So we were about halfway through physical properties. I believe it is lecture 5. That's on Laulima. That ought to be next to this. Great. We ended up with this nice little picture of a macro aggregate, right? So at our large scale, remember, we have things like plant roots and plant hyphae, soil microorganisms such as mycorrhizae, mycorrhizal hyphae, little tendrils of the fungus present in the soil, as being a biological driver of soil aggregation, okay? And then when we get into our smaller, and when we zoom in a little farther, we see that a lot of those agglomerations are held in microaggregates, which have their own little pore space and organic carbon inside, right? Water that's not always plant available, carbon that's not available to microorganisms, right? Because it's sealed up essentially inside microaggregates, and we like that for carbon sequestration, right? Or in this case, allowing the carbon that is still in the soil to remain there, right? By preventing microbial access. Great. Okay. So what I was pointing out, this is a macro aggregate, okay? We're going to zoom from out to in, okay? So we're going to look at some of the major binding agents that are contributing to these aggregates holding together, okay? So I recognize that this might be a little far away to do this on the screen, but just try and use this as a complement, okay, to the online resources that are on Laulima. Great. So when, as I mentioned, at a more coarse scale, looking at macro aggregates, etc., right, we mainly have roots and mycorrhizal hyphae being the binding, aggregating agent, okay? When we get a little closer in, okay, we have a little micro aggregate, which is, as we see, a package of clay particles, a hypha, right, a singular. We're on the scale now looking at an individual hyphal unit, okay, and a little bacterium that are doing some of those biological processes, such as producing exudates of organic materials that are then binding together colloids or particles in the soil, right? Zoom even farther in, we have mixes of humic or organic materials with clay, minerals, and our binding agents there are microbial and fungal debris that are encrusted with inorganics such as cations, right? They're doing a little bit of that cationic bridging, okay? Zoom even farther in, now we have a clay colloid, or a unit, right? A unit of clay. This is a unit of a 1-to-1 silica tetrahedral to aluminal octahedral kaolinitic clay, for instance, right? And we also have cementing agents that we have here in our andisols in Hawaii, okay? So again, our agents here are amorphous aluminosilicates, oxides, and organic polymers are sorbed onto clay surfaces, which produce electrostatic bonding and flocculation, okay? So those electrostatic bonding, right, and cation bridging are more the mechanism for micro aggregates as opposed to macro aggregates, which are more held by what? There's nobody in this room and it's only me, so I'll answer. By plant root hairs and mycorrhizal hyphae. Perfect. So here we just have a nice comparison, juxtaposition, okay, between clay aggregates, which can come up to the size of an individual sand grain, for instance, right? and an agglomeration of coarse sand grains, okay? Main thing taken away from this, right, is that clayey aggregates is labeled here, intraped micropores, okay? They have micropores which are able to mainly store water, okay? Both have macropores, which, as we remember, is more an indication of percolation, okay? Water infiltration, right, is up with more macropore space, right? So we're still gonna have nice water infiltration and percolation, right? Lessen our chances of erosion, right? From our soil getting saturated and puddling water on the surface and then going downhill and carrying soil with it, okay? But then we also, with aggregates as opposed to sandy soils, the added benefits of the micropores being able to hold water, okay? This is a table of the effect of cultivation over time in years, okay? This field has been cultivated, as in tilled, right? Row crops, right? For 100 years, 47 years, 32 years, 27 years, 15. We have organic matter percents, our aggregate stability, which is essentially a measure of the presence of aggregates, right? The degree to which they're there. And we have our infiltration rate, or in this case, it's percent of total rain that's infiltrated. Okay? So, off the bat, what can we see? Again, it's only me, so I'll go ahead and keep talking to myself. We have organic matter going drastically down with increasing time in cultivation, okay? That'd be a great question, right? What is the effect of what is the effect of continued cultivation over time on organic matter of a soil, right? As we can see, with increasing cultivation and increasing time under cultivation, we have decreasing organic matter. Ooh, why is that? I would definitely be trying to wake people up in class asking why that is, right? But we ought to know by now that's because with the active tillage, that's doing a couple things, right? It's bringing more anoxic, which providing oxygen to areas that have been oxygen limited, right? And when that happens, of course, we have oxygen being supplied to aerobic microorganisms that have been present in the soil, yet hibernating in a sense, right? All of a sudden they have access to oxygen because that tilling has brought up subsurface soil onto the surface. Excuse me. And then our microorganism population goes up. They feast down on all the present organic matter that was still there, at least some of it, right? And that organic matter that was stable in the soil in some of these micropores, right, which have been broken physically from tillage. And they have access to that organic matter, they eat it up, they die off, and we have organic matter going up into the air as carbon dioxide. Okay, so our leakages. We've mentioned a couple times that, well, hopefully we have, right? That organic matter is very important when it comes to aggregate stability, okay? We just looked at some of those previous slides that showed things like mycorrhizal hyphae and root hairs holding together macro aggregates. What are mycorrhizal hyphae and root hairs? Ding ding, organic matter, exactly right. So when we lose our organic matter from continued cultivation, right, especially if we're doing high tillage, right, annual cropping, right, where we're really working the soil regularly every year, okay, we lose a lot of our organic matter due to increased microbial respiration and activity, okay, which is kicking off the CO2 into the air. And what that does is takes away a lot of our old organic matter that was actually acting in those biological means to physically bind, biologically physically bind soil aggregates together, okay? And so then, as we would expect here, right, our infiltration is going down. Our water infiltration is going down with increased time under cultivation. Sorry, I'm gonna make sure this thing doesn't fall asleep right here. Oh. Great. So, like I said, this connection should be clear by now, okay? That with decreasing aggregate stability, we also have a decreasing of water infiltration, okay? Because with less macro aggregates, okay, our macro pore space, which is the main driver of water infiltration and percolation, remember, right, are going to be decreased. And then our infiltration is going to also be reduced. Great. With increasing cultivation, soil organic matter declines, and then aggregate stability declines, and water infiltration declines, and soil erosion increases. Okay. As I've mentioned with surface area being a constant theme, mentioned by now, I think that organic matter is a fairly constant theme, right? We'll see it. So if you are dealing with a soil with low aggregation, right, high dispersion, that is not infiltrating water very well, okay, here's where we get to our rubber hitting the road moment, right? Perhaps an application of compost, right, could help along some of those biological macro aggregate forming processes, which will then foster macro aggregates to come back into existence, which will increase our macro porosity, which will increase our infiltration and lower our soil erosion, right? Why do we care? Aside from not wanting to lose soil to erosion, right? We have a number of other important things associated with aggregation, right? It's not solely a water infiltration game, okay? There are other benefits of having good soil aggregation. So, well-aggregated soils have a mixture of macropores and micropores, doing three things. Count them, right? So our macropores are helping our water infiltration. That ought to be just about ad nauseum by now, right? Our micropores are enhancing our water holding capacity, okay? Which means that after one rain event with a number of micropores, your plant available water will be available longer, okay? And we're also increasing our aeration with good macropores and micropores, okay? Mainly in the macropore zone for this. What does that do? It enables some microbial life, right, activity to keep going along, right? We want air in our soils, okay? Low bulk density. Well-aggregated soils have that. So, someone has stolen my pen. Is this it? Well, remember here, a nice, well-aggregated soil bulk density, as we remember, right, is the mass, total mass, including pore space in a given volume, okay? So we have a nice macro aggregates here, which are then providing large macro pores, right, space. So all that space is counted in the bulk density. So with nice big macro pores, we have a essentially lower bulk density, right? As opposed to if we didn't have nice macro aggregates or any kind of aggregates, right? I don't even have the time to draw all this in here, right? Essentially, all of your pore space is gone. So your mass per given volume is much higher, right? Exactly. As you can see here, right, our macro pores are going to be pretty much gone, okay? Our water infiltration is going to be crummy. This happens in some instances with dispersed soils, with very high clay content soils, same thing, our drainage can really be an issue sometimes. So the other problem, aside from water infiltration, okay, with not having good aggregation and having a higher bulk density, is it's harder for roots, okay, to actually negotiate this mess, right? You're also looking at what's a nice agronomic example is corn, right? What's the old saying? Corn doesn't like wet feet. You get a soil with no aggregation, right? With no water infiltration, or percolation, or drainage, right? This is going to fill up really quick with water, and then it's going to pool on top and go down. But then it's also not going to drain, okay? So then we're going to keep our roots perpetually wet, right? Which is a huge problem in terms of getting root infections from pathogens, okay? So drainage is super important. What's nice about low bulk density also is it's easier to work. It's easier to cultivate, right? I think I've used the example in class before. You use less gas tilling a well aggregated, aka lower bulk density soil than you do to till a high bulk density dispersed soil. Hopefully that's somewhat clear, because in a nice fluffy aggregated soil with a lot of pore space and low bulk density, it's easy for those tiller tines or discs or whatever having to move through the material, okay? Because it's moving through air also. In a dispersed soil, it's almost moving through just clay, right? It's tough. Also, resists compaction and supports traffic. Those go pretty well hand in hand. So when we have nice aggregation and nice good macro and micro pore space, okay, then we're resisting compaction because those macro pores are still holding up and butting up against each other really bluntly, and still that pore space, macro pore space, is resilient, right, to compaction. And it can support traffic because for the same reason. They maintain their space better, right? Bigger particles are harder to squish together as opposed to a bunch of really small ones already there, and you press them together and all of a sudden we're compacted, right? They resist compaction, and hand in hand with that can support more traffic, okay? So a nice example is the cane roads in Hawaii, right? That a lot of them were on anesols and oxazols, where we have pseudosands that are super strong macro aggregates, okay? And those pseudosands are able to maintain their shape and structure, essentially with large rains, right? Let the water go right through so the roads stay there when it rains hard. And then same token, they're able to support big old trucks and tractors going through there all the time, okay? All right, I'm gonna cut it here, and I'm gonna try and keep these videos to not be full raging 50-minute activities, because I guess there's been a lot of research that after, I believe it's 5 minutes, everybody gets up and goes away. So we'll try and take this in manageable chunks, okay? I appreciate your all's flexibility and support and continued endurance, right, on your academic endeavors during this, challenging time, unprecedented time, okay? So please provide me with any feedback that you get from this. If you can't see anything for nothing, if you can't hear me, I'm going to try and get this transcribed. And I believe we'll still go with the lab time live check-in with Zoom. And so I'll make that all very clear and apparent and accessible there on Laulima. All right, wash your hands, stay healthy. Aloha kakau. Let me press the button.